Okay, here's a quick tutorial on DNA synthesis. So for DNA, we have, let's do this first. All right, for DNA, we have, it's a double strand, right? We know that there's two strands, and the two strands go 5' to 3' and 5' to 3'. They're in opposite directions. And what those prime numbers mean are referring to the carbons on the backbone of the sugar. So over here, this is actually ends in a OH on the 3' carbon, and on this side, there's a phosphate. Okay, and same thing over on the and there's an OH here, and over here there's a phosphate. Okay, so that's important. This is important right here. This particular 3' OH is important. Okay, and you'll see that in a second. So we always have 5' to 3' in opposite, what we call anti-parallel directions. So during DNA synthesis, this is going to open. Okay, helicase is going to come in and is going to open this up, right? This is what we call a replication bubble. Okay, so here's your 5' area, right? And this is 3', and this is 5', and this is 3'. Okay, so now this open area, and helicase enzyme has opened that. DNA polymerase comes in and binds to the replication forks. Okay, and so most of the pictures in your book have only shown, like half of this, right? But so DNA polymerase binds. Here's DNA polymerase. All right. It binds and it starts to go. So you have your DNA template. It kind of looks like this, right? Okay. So now you have, this is again 5', 3'. So this end over here is actually 3', right? So now anything that's going to be made, okay, any new strand that comes in, any new nucleotides are going to run, in this case, 5' to 3'. All right, so it's going to come in and it's going to, you're going to get addition of new nucleotides, right? But every time they add a nucleotide, right, there's going to be a free OH right there. Then a new nucleotide's added, and there's going to be another OH. So you always have a free 3' OH. Okay, why is this important? Why is this important? Important because you need a free 3' OH to add nucleotides. Okay, you need that. That's absolutely necessary. So in this strand, right, in this strand right here, in this strand, this we call the leading strand. Leading is 5' to 3', and as it adds, right, it's 5' to 3'. As it adds, it's always going to add, and it's going to add a nucleotide, and as it adds the nucleotide, it's still going to have a free 3' OH. Okay? How did it start? Well, where was the free 3' OH where it started? Well, that started with an RNA primer. Okay? So actually, this particular enzyme, so that's an RNA primer. Okay? So that primer starts the process, okay? And so where this opens, it actually starts and goes in opposite directions, right? So imagine that we started it like this, and imagine here's your opening, or the beginning. Let's say it starts to open right there at an area where it starts to open, right? So you only have 3 particular nucleotides open. That's where the RNA primer, and then it's going to extend out this way and this way in both directions. All right, so if it starts here and it also starts here, okay, here's your primer. As it moves towards the replication fork, okay, this again is going to be 3 prime, right, 5 prime, 3 prime, because it opened up that way. And this is towards the replication fork. It's going to be continuous. It's going to keep going, okay? But the other strand, this, like when you look at it, you know, when you only look at half, kind of, if you only look at half the bubble, if you only look at one replication fork, okay? If you only look at one replication fork, you have a leading strand and a lagging strand. This is your leading, and it's going to be continuous, and it's 5 prime to 3 prime, right? And it's going towards the fork. Now, the other strand is the lagging strand, and it's going to be discontinuous. Because as this opens, you're going to have you have a primer set here and a primer that's going to be there. Those RNA primers. And then from those primers, new strands get added. But eventually it runs into the primer again. Okay? So it actually forms a discontinuous segment. Right? These fragments are called, this fragment right here is called a Okazaki fragment. Okay? So you end up with these 2 strands, and then it will continue to open, and the replication fork will get wider while we're making the 2 strands, right? And then the other half of the replication bubble, because there's 2 forks, right? The other fork is kind of be like this, right? This is actually happening there, and this happens there. So you end up kind of flip-flopping. But as it moves within the replication fork, we're just looking in just half of what we're doing, half of the bubble. You're going to have a leading strand and a lagging strand. And the leading strand goes towards the fork. The leading strand goes towards the replication fork, while the lagging goes away from the fork. Hopefully that kind of gives you an idea, right? Because this happens in the middle of a strand of DNA. It doesn't necessarily happen at the end, and it happens at multiple places. And eventually, what you have to go back and do later is take out the RNA primers and replace them with DNA, and then also link together, fill in the gaps of those Okazaki fragments in order to have one continuous strand of DNA that's been replicated.